Thank you, everybody, for joining us on your Friday evening. My name is Mike Stickney. I work with the Montana Bureau of Mines and Geology. We're located here in Butte on the Montana Tech campus. The Bureau of Mines and Geology functions as the State Geologic Survey, and we have approximately 60 professional positions here, mostly in hydrogeology, geology. We have a water chemistry lab, and we conduct geologic and hydrogeologic studies around the state. My job is running the Earthquake Studies Office, which manages the Montana Regional Seismic Network. It's a network that consists of 42 seismic stations that report data in real time, and additionally, we get data from another 50 or so stations in the surrounding region. With that data, we locate earthquakes and blasts around the region and develop a seismic catalog. And so tonight, I'll be talking about some historic earthquakes that have occurred around Montana, some of the faults that we know about that are potentially active in the state, and then I'll touch briefly on the end on some recent activity that we've recorded. So with that, I will see if I can share my screen here and start this. Let's see, it says the host has disabled participant screen sharing.
Okay, let me just make you a host real fast, and then we'll be able to get you that screen.
Okay.
Right.
This is a very different presentation for me. I've not presented remotely before, but I guess the plus side is we don't have to worry about mosquitoes tonight.
Yeah.
There we go.
You should be a host now.
Let's see. So I guess I hit share. Yes. Okay. And I think we're off and running.
We are.
All right. So to get started, many times when I give a talk about earthquakes, everybody immediately thinks of California. And some people think that that's where all the earthquakes occur. It's true that many of them occur there, but and as you can see from this epicenter map showing earthquakes since 1982, so about the last 2 decades of seismic activity, there are a lot of earthquakes along the San Andreas Fault System, the plate tectonic boundary on the west edge of North America. It goes offshore in Northern California and is offshore until it gets up into Alaska. But of immediate concern to us is this belt of seismic activity that starts in southwestern Utah or southern Nevada. It extends north along the Wasatch Front through Salt Lake City, northward along the Idaho-Wyoming border, and then at Yellowstone National Park, it apparently splits into 2 branches. One branch extends due west through extreme southwest Montana into central Idaho. The other branch continues to the northwest through western Montana. So this is known as the Intermountain Seismic Belt. Sometimes this western arm of it is known as the Centennial Tectonic Belt. It's an area that has, as you can see, numerous earthquakes, most of them small. Historically, a few are large and damaging. There are many different faults along this belt, but it's not a single fault zone. It's a very complex area tectonically. So I mentioned the Montana Regional Seismic Network. This is a map that shows the stations in the maroon color are those which the Bureau of Mines and Geology operates. They extend from over in the Red Lodge area all the way up to just about to Kalispell, and more or less straddle this Intermountain Seismic Belt. The other stations shown in green on this map are seismograph stations operated by other agencies, the U.S. Geological Survey, the University of Utah, the Idaho National Labs, the University of Washington, the Alberta Geologic Survey, and that we record data from in real time across the internet. So we use all these stations, data from all these stations together to locate earthquakes that occur around the state. And here's an example of most of that data. It shows the Intermountain Seismic Belt here. These are the Bureau of Mines and Geology started reporting earthquakes, started an earthquake catalog in 1982. And so between 1982 and the end of 2019, we have recorded and located over 50,000 earthquakes. And they very nicely illustrate this, this northern part of the Intermountain Seismic Belt and the Centennial Tectonic Zone. The stars are the larger earthquakes that have occurred during this period. In 1983, there was a large earthquake, a magnitude 6.9 down near Challis, Idaho. It had a large aftershock, a magnitude 5.8 aftershock. In 2005, there was an earthquake down here just north of Dillon. And then in 2017, there was an earthquake near Lincoln. And I'll say a little bit more about that towards the end of the talk. In addition to that seismic activity, we also have about 80 faults which are documented in the U.S. Geological Survey's Quaternary Fault and Fold database. It's available online. These are faults that show geologic evidence of having produced large earthquakes in the past 2 million years. Most of them much younger than that, probably in the last few 100,000 years. And faults which have moved recently in geologic time are more likely to move again in the future, accompanied by a large earthquake. And I'll have to point out that most of these faults have never been studied in great detail. We don't know a lot about their movement history. About a dozen of those faults have had some trenching studies and other studies to evaluate how frequently and how recently they have moved, and therefore tells us something about their potential seismic hazard in the future. Using both these faults and the historic earthquakes, the U.S. Geological Survey has produced a seismic hazard map for the United States. This figure illustrates the Montana portion of the National Seismic Hazard Map, and the takeaway from this figure is that the warmer colored areas are more likely to experience strong seismic shaking. The values that are contoured there are percent of acceleration of gravity, which is the way that ground shaking is measured. Anything above about 15% G, is that shaking of that strength is capable of causing damage to unreinforced masonry structures, older structures. And certainly the threshold for a person feeling an earthquake shake is usually about 1% G. So virtually nowhere in Montana is immune from earthquakes, but most of the activity occurs along this Intermountain Seismic Belt and the Centennial Tectonic Belt. So let's go and look at what's happened historically. Often that's the best way to see what illustrate the hazards that face us here in Montana. The first destructive earthquake in Montana's history occurred in June of 1925. It was centered just north of Three Forks in the Clarkston Valley, just north of where the Three Forks of the Missouri River come together to form the Missouri River proper. This earthquake had an estimated magnitude of 6.6. It occurred after school was out on a summer evening, June 27th at about 6 in the evening. So schools, churches were unoccupied, which was fortunate. There were a couple, I think 2 minor injuries during this earthquake, but no fatalities. But it did cause a lot of damage. This is the church in Three Forks. You can see the upper wall of a multi-story masonry building is particularly vulnerable to seismic shaking. Here's the school at Manhattan, and it's perhaps the best example you'll see of why you don't run outside of a building when an earthquake is occurring. As you can see, the building stood up, the roof is still there, but the shaking brought down a huge volume of brick and mortar from the top floor, and it all fell to the ground in a zone that crosses the front porch of the building, which is about where you might be if you were running outside during the shaking. It's always best to shelter in place, duck, cover, and hold on if you can. Duck under a sturdy desk or a piece of furniture. Cover your head, wait till the shaking stops, and then go outside. The next major earthquake, and I should say series of earthquakes, occurred a decade later in 1935. These were centered in Helena, or very close to Helena, and they began in early October of 1935. The first widely felt earthquake occurred on October 12th, probably had a magnitude around 5.6 or so. It didn't cause serious damage, but on the October 18th, a magnitude 6.3 earthquake occurred. This map shows the area over which it was felt, the outer contour here. It was felt strongly in the yellow area, some minor damage in the orange area, and heavy damage in the red bullseye in the center there. And then this earthquake was followed 2 weeks later on the 31st by an aftershock that was almost as big. It had a magnitude of 6.0. And some pictures of some of the damage that accompanied this earthquake. This was the county poor farm. Again, the upper walls of masonry buildings did not fare well. There were a few buildings that suffered total collapse, but there weren't many of those. Up to 60% of the buildings in the city of Helena sustained structural damage. Only a handful of them collapsed, but many of them were damaged. Here's an example of a residence where the entire front walls, upstairs, downstairs, fell outward, crushing the porch. Amazingly, the hot water heaters are still standing in place. Here's a building that suffered severe damage to an entire wing. It looks like somebody's kind of been propping up a few boards trying to maybe hold some of this brickwork up, but obviously this building was a total loss. There were 4 fatalities during this earthquake sequence, 2 during the October 18th earthquake and 2 during the October 31st earthquake. They all were as a result of falling building debris. The heavy masses of bricks coming down on unsuspecting bystanders is the most dangerous part of earthquakes in this part of the world. This is the State Armory building. This is a building that was designed to go into service during an emergency. Unfortunately, the structural damage was so severe that the building was condemned and later torn down. This is the Nabisco Bakery building in Helena, out by what is now the airport. Again, building was a total loss. And most amazingly, this is the Helena High School. This building was brand new on August 1st of 1935. This is how it looked on November 1st. This entire wing of the building collapsed completely, and it is just so fortunate that that first earthquake occurred at about 9 p.m. when the school was empty. A number of schools in Helena were severely damaged, and temporary classrooms were set up in rail cars that were parked on the siding. Most of them had coal stoves that were put into them, installed in them to provide some heat, but the school kids that year spent the winter months going to school in train cars. The largest earthquake in the state's history occurred in 1959. It was centered down just north of Hebgen Lake, near West Yellowstone. This earthquake had a magnitude of 7.3. It was the only historic earthquake in Montana where the slip on the fault that produced the earthquake propagated all the way up to the surface of the earth and formed what is called a fault scarp, this break in the ground surface where the closer side dropped down, the mountain side went up. That's actually how many of the mountain ranges in western Montana formed, is through this type of normal faulting. Here's a view, a close-up view of this fault scarp on the north edge of Hebgen Lake. It was up to 21 feet high, and here's a geologist for scale. It's a truly spectacular fault scarp, and very complex as it was later studied. Rockfall was a huge problem. The strong ground shaking and steep mountainsides sent lots of boulders crashing down. And here's an aerial view the morning following the earthquake. Here's Hebgen Dam right here, Hebgen Lake looking off towards West Yellowstone. And this white line that you can see along the edge of the photo on the left here is the fault scarp. That's the break. And so the fault was dipping down beneath the reservoir in the dam. In fact, the whole lake basin tilted towards that fault scarp because this lower portion moved down. You can notice a large landslide that took out part of the highway right here. There's smaller landslides that came down onto the dam and into the reservoir. And you can't really see it in this picture, but there were several waves that overtopped the dam and caused tremendous damage to the spillway to the point that it had to be rebuilt. This is a picture shown along the crest of the dam. It was a earth-filled dam with a concrete core wall. The dam did remain intact. It held water, but it was severely damaged by the severe shaking, with the fault being just a few hundred yards up the hill from the structure. One of the most spectacular effects of the earthquake was the Madison Slide. This is the lower end of Madison Canyon. We're looking west. The southern Madison Valley would be just out here to the west. And this entire section of the south wall of the canyon was shaken loose and formed the largest seismically triggered landslide in historic times in the North America. And it actually rode 400 feet up onto the opposing valley wall. Right down in the foreground here was known as Rock Creek Campground. It was a Forest Service campground, and there was an overflow area that extended downstream. There were 26 casualties at this site, all because of this landslide. Across the valley over here near Cliff Lake at another campground, rockfall came down and killed 2 campers at that site. And then 40 years after this earthquake, the remains of a missing climber was discovered melting out of the toe of the glacier at Granite Peak, about 30 miles to the northeast of this site. And it's surmised that this lone mountaineer was caught in a rockfall and buried on the glacier. And so he would have been the 29th victim of this earthquake casualty. Okay, I showed this map showing where the faults occur. Let's go in and take a look at a few of them and see what they look like on the ground. This is an aerial view looking at the base of the Madison Range. We're about halfway between Ennis and Madison Canyon. You'll notice this break that runs across the hillside here where the snow has melted off on the steeper faces. This is an old fault scarp from a prehistoric earthquake that occurred along the Madison Range front. If you follow that fault a little bit further to the south, it crosses the mouth of Wolf Creek, and clearly offsets these deposits that come out of the valley. This whole area of rumply looking topography is the glacial moraine that was carried out of Wolf Creek during the last ice age and left behind when the glacier melted. And so we can see that the glacial deposits are offset, therefore that this earthquake, perhaps more than one, has occurred since the end of the last ice age, which in this area would probably be on the order of 12 to 15,000 years ago. So 15,000 years sounds like a long time, and it is on a human time scale, but on a geologic time scale, that was yesterday. And the Madison Fault is very clearly an active fault that is likely to produce an earthquake at some unknown future point. Here's another example of a young and active fault. This is looking west at the Tendoy Range, where this is Interstate 15, just north of Lima, Montana. And this steep break that runs along the base of the range, and as far as you can see here, is the trace of the Red Rock Fault. The Red Rock Fault, we actually dug a trench across this fault back in the mid-1980s and estimated an age of the last movement of this fault on the order of 3,000 years ago. We couldn't find easy material to age date, but soil samples indicated that it was probably about 3,000 years ago. And we know from other relations that there was probably one additional earthquake, one earlier earthquake that occurred just after the last ice age. So probably two relatively young seismic events along this fault. Here's an aerial view looking at the same fault, the Red Rock Fault. This is Big Sheep Creek going west into the Tendoy Range. Here's a car on the road for scale, if you can see my pointer right there. And this break running all the way across here is that fault scarp. And it's a big fault. It's too large to have occurred in a single event. It represents multiple earthquakes that have occurred along here. Recent studies have indicated that anytime an earthquake is big enough for the fault to rupture up through to the surface, you're probably talking about an earthquake that's at least a magnitude 6.5. Smaller earthquakes, 5.5, 6, certainly still strong enough to do damage if there are cities or buildings nearby just from the shaking. But it appears that you need at least a magnitude 6.5 earthquake to cause surface rupture like these old fault scarps record. I mentioned fault trenching. This is a example from down on the fault near east of Canyon Ferry Reservoir, Big Belt, along the front of the Big Belt Mountains. And this was a U.S. or Department of Reclamation, U.S. Department of Reclamation trench. And they went in and dig a trench and leave a vertical wall. And then within that wall, you can see the exposed layers, and then go in and carefully look at where those layers are offset, make a very detailed map. Here's an example from a trench in the Lima Valley, Lima Reservoir Fault in the Centennial Valley, east of Lima, Montana. And you can see there are layers that are broken up and offset, cut off, and then other layers, mainly in this case, windblown sand and silt, that were deposited on top of the faulted materials. And by unraveling the stratigraphy, restoring the offsets of these layers, we've estimated that there are 6 to 7 surface faulting events in this exposure. So these faults move repeatedly, often with thousands, perhaps even tens of thousands of years of time elapsed between these very large earthquakes on a specific fault. And then recently, a new tool has come to light to study faults fault scarps. It's known as LIDAR. If you're not familiar with that, it's a technique where an airplane flies over. It has a device that flashes laser light down at the ground and measures how long it takes for that light to return. And it's fairly complicated process, but when the data are all collected and processed, you get a very accurate map, an image, digital elevation model of the Earth's surface. And then you can illuminate that just with artificial lighting. And you can think of it as a view of the ground surface after the apocalyptic forest fire that burned every stick of vegetation off the ground, so you don't have to look through the forest. This area is down in the Bitterroot Valley between Victor and Hamilton on the west side of the valley. These deposits over here on the left that come out to right about here are glacial deposits from a glacier that came down the valley that's just out of view to the left of the screen. And then these, this big terrace deposit, and you can see some remnant stream channels on it. That was the outwash plain. When that glacier melted away, it washed a lot of sand and gravel down out into the basin, formed this big outwash plain. And then this red line marks a fault that offsets the outwash plain. And over here, this profile, a topographic profile is shown in the lower right here. There's on the order of 12 feet of offset on this surface. And up here, in an older material, there's almost 80 feet of offset. So this surface is clearly younger than up here. The differing amounts of offset on surfaces of different age indicate that earthquakes have occurred there repeatedly through geologic time. And just one other interesting aspect here, you can notice some little horizontal bands here on some of these slopes. Those are the shorelines of glacial Lake Missoula that flooded back up into the Bitterroot Valley this far and left these little remnant shorelines. And they're visible on this LIDAR data. That's how detailed it is. It shows very small, subtle features, even in forested areas. It's a wonderful tool. Okay, let's talk about some recent activity. This is a epicenter map showing the area just to the northwest of Helena. You know, the town of Helena would be right in here. It's Canyon Ferry Reservoir and the Missouri River. The red lines mark faults that that have been mapped as part of that fault map that I showed earlier. And you can see that there's scattered activity, even clusters of activity all through this zone. This would be the Intermountain Seismic Belt in here. Well, on July 6th of 2017 at 12:30 a.m., a magnitude 5.8 earthquake occurred right here, the star. And then in the subsequent two and a half years, we recorded and located about 4,000 aftershocks that occurred in response to this earthquake. And here's a little closer view of that aftershock zone. The town of Lincoln would be right here. This red line is Highway 200. This is the Avon Valley here. Avon would be south of the valley, and Helena would be off here to the southeast. The red dots show earthquakes over magnitude 4.5, and you can see that they're scattered out. They form a fairly dense cluster here that seems to show a little bit of north-south elongation. It turned out that the fault that ruptured during the main shock was a north-south fault, and it was a strike slip fault. It was a fault where the left side went south and the right side went north. It was a little bit of a surprise for us. Well, if I back up one slide, you can see that there aren't any mapped young faults in the area. There's faults here on the north edge of the Helena Valley, up here in the Hilger Valley, but nothing right in the immediate vicinity of these earthquakes. That turns out to be very common, that earthquakes earthquakes in the Intermountain Seismic Belt, except for the very largest one and a handful of other ones that we have enough data to demonstrate that they occurred at depth on a fault. Most of these routine earthquakes, small to moderate sized earthquakes, are not occurring on faults that are mapped at the Earth's surface. These earthquakes occur typically on the order of 5 to 15 kilometers below the surface, so 3 to 10 miles deep, which is shallow in terms of earthquakes around the world. And these shallow earthquakes seem to produce a lot of aftershocks. A later study by a student at the University of Montana, a graduate student at the University of Montana, showed that some of these other clusters that occurred off to the west, well away from this zone, were similar little northerly trending strikes of faults. And this zone appears to have responded to something called bookshelf faulting, where overall the rocks to the north are moving to the right, and to the south they're moving to the left or west, and there's a series of smaller breaks that are slipping in response to that overall right lateral strike slip movement affecting this whole portion of the Intermountain Seismic Belt. So as I mentioned, over 4,000 aftershocks. They've slowed way down. We're currently seeing, I don't know, maybe a half a dozen per week, and mostly small aftershocks, but we're still seeing a few earthquakes that are occurring in this area. Here's a map of, if you do Google, did you feel it, you'll come up to the USGS website where you can report your, if you feel an earthquake, you can go in and fill out a little questionnaire, and it collects your data and compiles it along with everybody else who reported, and produces a map similar to this. Brighter colors mean stronger shaking. On the map, the live map, you can actually go to these funny looking polygons are zip codes, and you can go to each zip code and click on it, and it will give you the number of people that felt it and what the average strength of shaking was. For this earthquake, there were over 19,000 felt reports, and this is sort of the way that it's done now. Instead of using zip codes, they use little 6 by 6 mile squares and compile the data in smaller, more regular areas. But this earthquake, people reported this earthquake all as far south as Salt Lake City, as far north as Edmonton, Alberta, out to the Pacific coast, and just about out to the Montana-Dakota line. And so it was felt basically throughout the entire northern Rocky Mountain region and beyond. This is a seismogram, a record of ground shaking recorded by one of our closest seismic stations. Each horizontal line here is 15 minutes of time, and when you get to the end of one line, you drop down a line and go across again. It's like lines of text on the page of a book. It starts at the top, goes left to right across the page and down, and the times are labeled over here. These are hours, the date and the hours, and so 24 hours. Every one of these little blips, and the bigger ones, of course, are aftershocks that occurred immediately following the main shock. And 4 days later, the same station, you can see it's much less busy, but there are still literally hundreds of small aftershocks that occurred here, and still quite a few larger events. Aftershocks are very, very typical after moderate and large earthquakes in this region. Shaking, as I mentioned, it shook a good part of western Montana. This was a grocery store in Helena. I guess it's time for a cleanup on aisle 5. In Butte, as I mentioned, this earthquake occurred just after midnight, which was a good time. The streets were quiet. This happens to be photograph taken at the Montana Folk Festival, which occurred 2 days later. And this is the Napton Apartments. And if you look way up here at the top, there was a ornamental detail with granite block and brick. During the earthquake, big chunks of granite came off, fell 4 stories, and landed right down here on the ground. And so it was very fortunate that this earthquake occurred when it did, and not 2.5 days later. There was fairly strong ground shaking up in the mountains to the southeast of Lincoln, but no ground rupture. This earthquake apparently wasn't quite big enough to produce that surface rupture along the fault. The shaking did cause some slumping in loose and unconsolidated road fill material, as you can see here, but this is mainly shaking of loose unconsolidated materials on a steeper hillside. And we did sustain some damage here in my office, but we were able to repair it. Another recent seismic sequence occurred near Manhattan, Montana. So Lewis and Clark Caverns is right over here on Old Highway 1. Here's Three Forks and Bozeman down here. Little town Manhattan is kind of midway between. And in late October of 2018, small earthquakes started occurring there. And they continued on for probably the better part of 18 months. During that period, there were over 850 earthquakes that we located in that area. 4 of them were moderate sized, ranging between magnitude 4.7 and 4.0. Had 15 earthquakes that were in the magnitude 3 range, and 43 earthquakes that were big enough that local residents felt and reported them. So there was no fault at the surface mapped in this area. It was there's obviously 1 or more faults at depth down there that decided to slip for a while. An earthquake swarm like this is a sequence of earthquakes that there isn't a single outstanding main shock followed by aftershocks. Rather, it's a group of many earthquakes clustered in time and space without a single outstanding earthquake or single much larger earthquake. So the example of an earthquake swarm near Manhattan. It's pretty well died down now, but I do occasionally see small events that are still occurring in this area. And then most recently, on March 31st, a magnitude 6.5 earthquake occurred over near the town of Stanley, Idaho. This would be central Idaho, along that kind of the middle of that centennial tectonic belt that I mentioned previously. The small town of Stanley is right here in the Sawtooth Range, very scenic range of high glaciated mountains just to the south. The main shock occurred up here, and then aftershocks, the early aftershocks occurred in this zone, both north and south of the main shock epicenter. But over in recent weeks, this branch or arm of aftershock activity extending out to the east has developed, and then subsequent to that, some of the activity extended down into the Sawtooth Range. And so this again was a strike slip earthquake. Even though there's a huge normal fault that uplifted the Sawtooth Range and down dropped the Stanley Valley, this recent earthquake was a strike slip earthquake with horizontal movement on a vertical fault. It occurred when there was a large snowpack in the area, but to date, none of the geologists that have worked in the area have discovered any evidence of surface faulting. We're right at that kind of threshold magnitude where it wouldn't be surprising to find some minor offsets, but thus far I'm not aware that anybody has identified surface deformation. The other complicating factor is this earthquake occurred during the pandemic, and so traveling to and from other states was not an easy thing to do. The folks at Boise State managed to get a number of seismographs deployed in the epicentral area, and those stations are still out there collecting data as we speak. And as you can see, we've had over 1,000 aftershocks thus far, and those are just the ones that have been located. Our seismic system, our seismic recording system, has triggered more than 4,000 times in the last 2+ months on aftershocks from this sequence, and in fact we had a magnitude 4 aftershock there this afternoon. Almost 200 earthquakes in the magnitude over magnitude 3. So this has been a very prolific aftershock sequence, and we haven't seen the last of it yet. It's still going strong. So this is a plot that shows earthquakes above magnitude 5 through time in Montana. Our first earthquake that was reported was in 1865 in Helena. Based on the strength at which it shook, it was estimated to have a magnitude of around 5. In the first couple decades of Montana history, it's possible there were some magnitude 5 earthquakes that were missed just because there weren't many papers going back that far. The area wasn't densely settled with people that left written records. But we think that since 1900, even though seismographs weren't in common use back then, that just earthquakes above 5, enough people would feel it that there would be a written record. So going on, this is a timeline of earthquake activity. That Clarkston earthquake I mentioned, the 6.6 in 1925 is right here. Here are the Helena earthquakes, the 6.3 and the 6.0 at foreshock, and some other associated activity. I didn't talk about the 1947 earthquake that occurred down in the southern Gravelly Range. It's probably about a magnitude 6.2, but it was in a remote area in the fall of 1947. In fact, winter had already set in, and so there was some broken windows of Virginia City and Ennis, but really no serious damage because it was so remote. The 1959 earthquake here, magnitude 7.3, I didn't talk much about its aftershocks, but it had several aftershocks that were in the magnitude 6.5 range. And then the Earthquake Studies Office and the Seismic Network opened in 1980, and since then we've only had 3 earthquakes above magnitude 5, none of them above magnitude 6. And so I guess by deploying a seismic network, we've done a fairly good job of preventing earthquakes in the region, at least so far. But the question remains, back in the middle of the last century, was this an unusually active period? And we're back to normal activity now? Or perhaps this was normal and maybe we're in an earthquake drought now? And the simple fact of the matter is we don't have a long enough historic record to know which of those, or maybe some combination, is the right answer. But it's clear from the ongoing low-level seismic activity and the faults that we see in the state that the potential for future large earthquakes is very real. And then this last figure here, this is a map showing population change by county in Montana since the 1959 earthquake. And blue counties have lost population. Yellow, orange, and red counties have gained elevation. And then plotted on top of that are the example of the recent seismic activity. And I think you have to come to the conclusion that people want to live where there are earthquakes. So if we're going to do that, we should be aware and take the appropriate precautions. And with that, I will attempt to answer any questions that you might have. Let's see here. If I stop sharing my scene, do I see is there, oh, there's a chat room here.
Mike, can you hear me?
I can.
Yeah, this is Wells Warren from Dillon.
Uh-huh.
We were sitting in our living room on March 31st when the Sawtooth earthquake happened.
Yes.
And we felt it as a series of thumps. And this was 6.4. It was quite an earthquake.
Yes, it was.
And especially now that we've looked at the records, but it only lasted about 30 seconds.
Maybe a little bit longer.
Yeah.
Yeah.
And,
is that typical?
Well, it probably is. Dillon would be certainly closer than Butte was, but still quite a few miles away. Seismic waves are like sound waves. As they travel, they lose energy. And so by the time the waves, they've lost probably most of their punch by the time they made it into Montana. But the other thing that happens is the waves, the wave train, the P and the S waves, separate from each other and they get spread out over a longer time window. So feeling that shaking for that 30 seconds or so, you were probably feeling the S waves and surface waves, which by that distance had spread out over a window of 20 or 30 seconds.
Okay. The other question I had was the sensation was unlike anything I could name. It was unsettling. It was almost like your stomach was turning. Is that typical?
That's a common reaction to seismic shaking. Many people find it disorienting, and it can cause a nauseous reaction just from, I think, I don't know if it affects your balance or your sense of verticality, but that queasy feeling is a common report to sometimes mild earthquake shaking.
Yeah. Thank you. This is fascinating.
Well, thank you for your attention.
I have a couple of questions for you.
Sure.
First of all, how does a batholith affect an earthquake or how you feel an earthquake? And are there any indigenous people's stories prior to 1880 documenting any earthquakes?
Well, in terms of the batholith, for those that may not be familiar with the term, that's the big molten mass of rock that cooled slowly underground and then gets exposed by erosion. So it's a big mass of granite. Here in Butte, we live near the middle of the boulder batholith, and it's granite in general is a very good conductor of seismic waves. It doesn't have a lot, I mean, it does obviously have some fractures, but it doesn't have a lot of different rock types. It typically makes a very good substrate to put a seismic station on. It's a good conductor of seismic waves. So seismic energy will travel quite well through it. With regard to the Indian lore about earthquakes, yes, it does exist. I don't have any information about oral histories of earthquakes here in Montana, but I know the West Coast, some of the West Coast tribes talk a lot about them and have oral histories. And I've been told that for those tribes in coastal Alaska and the Pacific Northwest that make totem poles, whenever you see a thunderbird, the thunderbird is the sign of an earthquake. And there are some papers that discuss oral histories of earthquake, of Indian, from natives about earthquakes. But like I say, I'm not aware of any for here in Montana.
Thank you.
Hey everybody, just a quick reminder that if you have a question, please put it in the chat. We're actually going to start winding down now. So Mike, if you want to pick out about 1 or 2 more questions, I think we're going to start winding down the talk.
And this is just in the chat window?
Yes, it should be. Yes.
Oh, okay, here we go. So Amanda, why is the Ring of Fire a geological hotspot? Well, the Ring of Fire is a first order evidence of plate tectonics. The Ring of Fire really marks the edge of the Pacific tectonic plate, where it interacts with various other tectonic plates around the perimeter of the Pacific Ocean. And there are different types of plate boundaries. Probably the most common one is what's known as the subduction zone, where the oceanic plate is moving towards land, towards the continent, and being thinner and denser, it usually gets shoved down underneath the continental plate and driven back into the Earth. And it actually gets down deep enough that it heats up from the natural heat of the Earth's interior. It's saturated with water because it's been at the bottom of the ocean for millions of years, and it usually drags down some water-saturated sediments with it. That all melts and makes its way back to the surface as volcanic activity. And so Mount Rainier, Mount St. Helens are example. The Cascade Range in the Pacific Northwest forms in response to that subducting oceanic plate just offshore in the Pacific Ocean. In other places like California, instead of having a subduction zone, you have a strike slip or translational zone where the Pacific plate is moving northwest relative to North America, and you don't typically get volcanic activity associated with that type of plate boundary, but you do get very large earthquakes. And certainly the 1906 San Francisco earthquake and the ongoing seismicity in California is an example of that. Let's see, why am I surprised that there were strike slip faults in my examples? Well, that was a good question. If you look at a geologic map of east central Idaho, southwest Montana, all the big mountain ranges, the Lost River Range, the Lemhi Range, the Beaverhead Range, the Tendoys, going all the way over to the Madison Range and the Big Belt Mountains in Montana, all those are normal fault mountains formed along a normal fault where the mountainside went up, the valley side went down. And they are responding to extensional forces. It turns out that most of western Montana and central Idaho are slowly being stretched in a northeast-southwest direction, extended. And instead of just opening big cracks, you get these normal faults that take up that extensional movement. And it is possible to get strike slip faults in that geologic setting, but we hadn't really seen evidence of active strike slip faults in this part of the world. Clearly they must exist. They're harder to see because they don't leave a vertical offset in the ground surface. And so I guess that's why it was surprising to me to see these moderate to large earthquakes occurring along unknown strike slip faults. And let's see, anybody else here? What causes a quake to feel like shaking and others feel like rolling? Well, as I mentioned earlier, the seismic waves attenuate as they travel away from the source. And so usually if you feel a real sharp shake or hear a boom or an explosion, that's usually a sign that you're relatively close to the epicenter. And the rolling motion is more typically reported for earthquakes, bigger earthquakes that they're a long ways away, and the waves have traveled some distance, lost a lot of their high frequency energy. And so what's left behind is that more rolling motion.
All right.
And thank you for the kind words, everybody. I hope you enjoyed it.